So now it's time to move on to the next layer in learning about NMR spectroscopy, the so-called two-dimensional NMR spectra. Now in reality, all NMR spectra are two-dimensional. On the x-axis there's always frequency in units of ppm. On the y-axis there's always signal intensity. The 2D NMR spectra really refer to spectra that have two frequency axes. Here's one we are going to look at in the next few minutes. And all I want you to notice about it right now is that there is a carbon frequency axis. Here it's the y-axis, and the proton frequency axis on the x-axis. And then there's a bunch of spots. We've seen spots like this before, way back at the very beginning. Well, here they are. This is a two-dimensional NMR spectrum where it has two frequency axes. So I'm going to use as my way of introducing the use of these two-dimensional spectra, walking you through the solving of a rather interesting and rather difficult unknown. The molecule is not a trivial one to solve, but it does nicely illustrate how so much of what we've been learning so far comes together and complements the information we get from the two-dimensional NMR spectra. And let's face it, while it is compelling and fascinating to watch me solve one of these unknowns, ultimately it's going to be your job to be able to apply all of these ideas and start learning about unknown chemical structures on your own. So here's using this as kind of a nice worked out example from start to finish of figuring out the structure of an unknown based upon multiple NMR spectra. As we've done many, many times, the spectra themselves are on the course website, and if you haven't been in the habit of getting those things in front of you as you go through some of these videos, oh, get them now. This one is the most critical one to have these. And this is going to be a time when you're likely going to want to, watch a video, stop it, back up, look at something again, write things down on your paper copy of the spectra, write them all down, scribble all over the place on these things. That's what I do when I'm examining them. You can always download another copy, you can always print another one. That's easy. This one is definitely not the time to be shy about having copies of these things in front of you and writing notes all over the place on them. Now, whenever I show these two-dimensional NMR spectra to students, either helping research students in the NMR lab or in the context of the face-to-face version of this class, I find students when they first learn these go, oh, these are really neat. I'll start my analysis here. And no, I hope you kind of gotten the idea by now. No, you never start with the most complicated looking thing. You always start with the basic things and work your way up. That's why I've tried to present it, kind of in a step-by-step, learning to drink from the fire hose kind of manner. It's so we are not going to see the 2D spectra first. We're going to save them for last. We're going to look at the proton and the carbon and apply all the different ideas that we've been building on for the last several weeks in gleaning bits of information and fragments of structures until finally we have enough information to put the entire structure of this compound together. So here we go. We're going to begin with a sample history. The substance that we are going to examine is a white crystalline solid. It does not dissolve very well at all in chloroform. It did, however, dissolve well in DMSO, dimethyl sulfoxide. It's interesting to note that very fact. DMSO is a highly polar solvent, and in fact, if you may remember it from organic chemistry or organic chemistry lab, this is a solvent that is really good at dissolving a lot of compounds that are very polar and often hydrogen bonded when you want a solvent that is itself not a hydrogen bonder. It is sometimes referred to as an aprotic solvent, meaning that it will not hydrogen bond with the stuff that you dissolve in it, not the way water or ethanol might. But it is polar enough that it dissolves very polar compounds. Chloroform is polar, but it does not dissolve really polar hydrogen bonded compounds very well. So right off the bat, just by what solvent this stuff actually preferred to dissolve in, tells us or gives us a clue, a little bit at least, about this compound. We're going to be on the lookout for the potential of a substance that is a hydrogen bonder. The other bit of information we have available to us is the molecular weight. The results, let's say, of a mass spectrum analysis. And the molecular weight of this compound is 154 grams per mole. It's a modest sized molecule, not super large, but not a tiny little one either at that molecular weight. That is our sample history, and now we move on from there. And of course we begin with the proton spectrum. Here is the full proton spectrum, and I showed this simply to give you a feel for. There is the solvent peak, the DMSO solvent peak. It is a pentet, even though I haven't expanded it much here. If you had it on a computer screen, you'd see that fairly well. This is the solvent position for DMSO. We also see another peak nearby. This is water. This is a fairly wet sample. This is the position water takes in a solvent like DMSO. The fact that the sample is relatively wet gives a little bit more evidence that the molecule we're analyzing, the one at 154 grams per mole molecular weight, could well be a hydrogen bonded molecule and hydroscopic. It's such a good hydrogen bonder that over the time it's been stored, it's been around a while, it has been absorbing water out of the atmosphere. And so the crystals of the material, while not soaked in water, actually probably have a fair amount of water on them. So now we look at the number of groups of hydrogens and their integrations. One of the very first skills and interpretation we started working on in this class. The proton spectrum seems actually relatively simple. There are 5 groups here, ignoring and in fact expanding the spectrum so we don't see the water or the DMSO peak. We see 5 groups, and it's interesting, they all integrate the same. They all integrate to equal ratio, here presented at 1 to 1 to 1 to 1 to 1. And so all of our different groups, have the same number of protons in them. Now we turn our attention to the chemical shifts. There are no signals outside of the solvent and the water upfield from this one here at 4.5. And the most downfield peak is over there at about 8.7 ppm. There are no other signals further downfield from there. So this sample has pretty de-shielded protons in it. There's nothing highly shielded in this thing. The chemical shifts are interesting. 4.5 is our sign of a hydrogen near a heteroatom. We've seen them plenty of times near oxygens in the realm around 4. At 4.5, it's a little on the high side, but it's still within range. So we're going to keep that hydrogen near oxygen or other heteroatom in mind. We do see a set of peaks that have a beautiful chemical shift for an alkene here between 5.5 and 6.5 ppm. They do seem to have an interesting coupling pattern, but we're not going to get ahead of ourselves. We'll look at that in a moment, but right now we are inventorying our chemical shifts only, and we're going to call these the chemical shifts, potentially an alkene region. And then we have this last one over here at 8.7. Now that is pretty far downfield. The chemical shift first made me think about an aromatic ring, because they can be 7 to 8 and sometimes going up higher than that. It can be kind of variable. But there's only, it seems, 1 proton down here. We don't getting the 4 with 2 substitutions or 5 with 1 substitution on a benzene ring that we've seen plenty of times by now. And so we're going to be on the lookout when we look at the carbon spectrum. If this is a highly substituted aromatic ring, a benzene with 5 different substituents and say only 1 proton on it, which is certainly possible, even though we won't see the protons in the 7 to 8.5 ppm range, we will certainly see their carbons. So we'll be on the lookout for that. This is an intriguing position. 8.7 is pretty downfield for a peak in a proton spectrum, especially if it's not from an aromatic ring. And now the coupling patterns. We see a couple of triplets, the one at 4.5 ppm and probably with a small coupling constant, the one up there at 8.7 ppm. It's a little bit mushy looking triplet admittedly, but it does seem to be fairly clearly a triplet. It's kind of interesting in that both of these must have 2 protons, neighboring protons nearby to give a classic triplet pattern. In the alkene region, oh, this is gorgeous. This is textbook alkene coupling. And in fact, if you examine the coupling constants of these things, some of them look like doublets of doublets. And examining the coupling constants here does reveal a 17 Hertz coupling constant, a 10 Hertz coupling constant, and then the very small 2.4 Hertz coupling constant. 17 Hertz. That is most consistent with a trans-alkene coupling. 10 Hertz, beautifully consistent with a cis alkene coupling. 2.4 Hertz, small but consistent with a geminal coupling. Giving a pattern like these, they're all doublets of doublets. Here's a little diagram showing 3 alkene protons that would give this kind of pattern. And you can glean one other significant bit of information. As we've mentioned, they're all doublets of doublets. Even this proton is a doublet of doublets, it seems. 17 Hertz coupling constant trans, 10 Hertz coupling constant cis, but no others. In other words, whatever must be over here in the rest of the molecule, whatever's on the adjacent atom, that atom has no protons on it. If it did have protons, this thing would be a doublet of triplets, say. And we have seen that kind of pattern in other alkene molecules, but not here. So we have by lack of a coupling pattern, we have some interesting information as well. Now look at the homonuclear decoupling spectra. Here are 3 of them. We did 2 homonuclear decouplings on this thing. And it reveals something kind of interesting. If you decouple at that peak at 8.7, notice the peak at 4.5 collapses to a singlet, but the alkene region is left alone. In other words, our most upfield and our most downfield peak seem to be coupled to each other. And, as you might guess, if you use the decoupler in the alkene region, then the alkene peaks simplify and the doublets of doublets become doublets, just simple doublets. But you'll notice the ratios are very odd. Yes, indeed, there's a bordering first order to second order behavior. These are 2 chemically distinct protons, but they seem to have a chemical shift very close or within the order of magnitude of the coupling constant. There's that ratio, frequency difference versus coupling constant, and it seems to be hovering right around that magic value of 10, and we're seeing the onset of second order behavior, where the outer peaks of a multiplet shrink, the inner peaks grow. Kind of interesting to see that happen here. Now we turn our attention to the carbon spectra. Here's the carbon and the depth 90 and the depth 135. The carbon spectra shows nice, brilliant septet solvent peak like we would expect in a solvent like DMSO with methyl groups in it. That one we can safely ignore though for our purposes here, and we see only 4 carbons. Relatively small number of carbons for a molecule like this. The chemical shifts of 2 of the carbons are consistent with alkene up there above 120. We have a fairly downfield carbon here at 45 ppm roughly, and then another carbon up here at about 165, 166 ppm. Looking at the depth 90, one of these carbons is a CH, and only one. We already have a pretty good idea from thinking about a terminal alkene, and there was a CH in here. Here it is. Looking at the depth 135 shows us that there are two CH2s in this molecule, and that the carbon out here at 167 ppm is a quaternary carbon. There are no protons attached to it here. The peak disappears in both the depth 90 and the depth 135. Likely then a carbonyl, but it doesn't have the right chemical shift for the aldehyde or the ketone. More consistent with the possibility of it being either an ester, a carboxylic acid perhaps, though we didn't see anything way downfield in the proton spectrum that we would expect to see in a carboxylic acid. The other possibilities besides ester then would be perhaps an anhydride or an amide, acid chloride perhaps, although they're kind of rare and fairly highly reactive substances. So we have a carbonyl, but not quite sure. I think we can't quite say yet exactly what functional group is out there. But I want to call your attention back to the depth 135 just a moment. Two CH2s. Now remember, our proton spectrum integrated with 5 separate groups, all integrating the same. We assigned values of 1 to 1 to 1 to 1 to 1. But our carbon spectra, the depth 135 in particular, is showing us there are two CH2 groups in here. I wonder if this is an indication that the integrated proton ratios are not 1, 1, 1, 1, 1, but perhaps 2 to 2 to 2 to 2 to 2. If that's the case, then this is an indication that this molecule might have some symmetry in it, that we're getting a fairly small number of peaks, only 4 carbons, for example, but in a molecule of 154 grams per mole, 4 carbons doesn't add up to much there. But if it's a symmetric molecule, then 4 carbons would really be a larger number of carbons, 7 if the axis of symmetry is on the carbon, or 8 if the axis of symmetry is on a bond between carbons. That's something to keep in mind. This is a reasonably good indication that this molecule may, no guarantee yet, but may have some symmetry in it. And if it does have some symmetry in there, then look at our terminal alkene. It features these 2 protons that are chemically distinct, and then this one here trans to one proton and cis to the other on the terminal CH2 group. They would all give integrated ratios of 1 to 1 to 1. But we see CH2s and indication of symmetry. I wonder if this molecule actually has 2 of these terminal alkenes in it, and it would have a structural feature that would look something like this with other stuff in the middle. That'd be kind of cool. Well, keep that in mind as well. So here it is, the first 2-dimensional spectrum. This is called an HSQC, Heteronuclear Single Quantum Coherence or Correlation Spectrum. And sometimes I've seen them referred to simply as HETCOR spectra, Heteronuclear Correlation. It has 2 axes on it, the carbon spectrum on one side, the proton spectrum on the other. And in between you see spots. And the spots tell us the following information. Technically they tell us which protons are coupled to which carbons by the large direct 1-bond 130 approximately Hertz coupling constant between a carbon-13 and a proton attached to it. Look at the first correlation I've drawn in on the spectrum here. The fact that this spot is out here at this position tells me that this carbon at 45 roughly ppm correlates to, is coupled to, the proton at 4.5 ppm. In other words, this carbon and that proton are attached to each other. That is why we call it a heteronuclear correlation spectrum. Here's the second correlation I've drawn in, and this is one of the alkene protons correlating with one of the alkene carbons. I want you to notice here that the depth results that we've also drawn in here, because that's really important, shows that the alkene CH is attached to the one alkene proton that shows both the 17 Hertz and the 10 Hertz coupling constant. There's no doubt that we've identified this carbon, not the terminal alkene carbon, but the CH of the double bond. Then look at the other alkene carbon and notice carefully there is not one spot lined up with this carbon. There are two. The depth 135 already has told us this is a CH2, not a CH. And sure enough, it has two protons attached. But notice there's two spots, two protons of different chemical shifts. Sure enough, the cis proton and the trans proton are out there with different chemical shifts. And in fact, this marks them very nicely. We've seen, this is our first example, and this is one of the beauties of a HETCORE spectrum. It is very good at showing us CH2 groups that have two protons that are not equivalent attached to it. The other interesting parts about this spectrum are the potential carbonyl carbon at 167. You sure enough look at it and see there are no correlations to the proton spectrum here. Indeed, this is a carbon with no other, with no hydrogens attached, like a carbonyl would be outside of an aldehyde, but there's no evidence of that in the chemical shifts of the proton spectrum. But the other interesting one is this proton, the proton at 8.7 ppm. It has no correlating carbon. In other words, this is a proton not near a heteroatom, on a heteroatom. That's rather fascinating. We've seen hydrogens on oxygens at various positions and stuff. They can vary quite a bit depending upon the solvent and how wet the sample is and things like that. This one's all the way up at 8.7 ppm, and we have pretty good evidence that these integrations aren't 1 to 1 to 1 to 1 to 1, but 2. There are 2 heteroatom protons here. Now, think carefully about that for a moment. 2 equivalent heteroatom protons. How do you do that? You could put 2 protons on oxygen, but you get water. There's nothing else you can do with it. And this is not water. It suddenly starts to dawn on us, the heteroatom may not be oxygen. Because think about nitrogen for a moment. Nitrogen can be bonded to a carbon and take 2 hydrogens. That's kind of interesting. That would get us, if it's a carbonyl, an amide, which would have an unusual chemical shift. And we have a carbonyl that has a consistent chemical shift with that. But that leads to one other very fascinating puzzle. The peak at 8.7 ppm in the proton spectrum is a triplet. It's coupled to the peak at 4.5. Our homonuclear decoupling experiment has already shown us that. In other words, the hydrogen on this heteroatom has 2 neighboring protons. So even if it's a hydrogen on a nitrogen, it has to be 1 hydrogen on a nitrogen, because the nitrogen is connected back here to the carbonyl and then to a CH2 group to give the triplet. But that's ruined my integrations. Now I have a 2 to 1 ratio of protons here. Unless I remember the symmetry. What if the molecule has this as its core components? Carbonyl, NH, CH2, NH, carbonyl. And what if the molecule is perfectly symmetric? There it is. 2 nitrogens on a heteroatom coupled to a CH2, giving a triplet. The CH2 hydrogens near not 1 but 2 heteroatoms, nitrogens in this case, moving it up from around 4 to all the way around 4.5 ppm. They are triplets because they feature 2 neighboring equivalent protons. It's absolutely stunning when you start putting these pieces together what you can come up with. And in fact, we've already speculated about the terminal alkene and the potential of 2 of those. Now we combine it with the evidence here and we have a viable molecule when you put this whole thing together. And here's the kicker. If you add all the pieces up here, this is 154 grams per mole. This is the structure of the molecule. Now there is one other 2-dimensional spectrum I'm going to show you. These are actually a little bit harder to interpret than HSQC or heteronuclear correlation. And for this molecule, that really doesn't give us any additional information, but it's simple enough that it's a good introduction to it. This is the Homonuclear Correlation spectrum. It is simply referred to as a COSY, C-O-S-Y, Correlation Spectroscopy is the acronym here. Now these are kind of interesting in that you'll notice there's a diagonal line, and we'll talk about that in the next video, where that comes from. But you see, again, 2 frequency axes, this time both axes of the proton spectrum, and you see a bunch of spots in the middle. It's not the diagonal that's really important, it's the peaks off the diagonal. And I want you to see, for example, this peak here and this spot, how it links the proton at 8.7 and the proton at 4.5. This spot tells us those 2 hydrogens are coupled to each other. You can also see the same set of spots here off the diagonal for the alkene protons, as we might expect. They're all coupled to each other. We'll talk more deeply in one of the future videos about interpreting COSY spectra. They are actually a little bit harder to work with than the heteronuclear correlation, but they too can be a great source of information about your molecules. In many respects, the COSY experiment really is like a grand homonuclear decoupling. It really does all the homonuclear decoupling experiments you could possibly think of all at once in one spectrum, and that's where their power comes from. COSY spectra tell us which protons are coupled to which protons. In other words, which protons are near each other in the molecule. Together, we have gone through essentially every one of the techniques that we've been developing here in coming up with a structure for this molecule. It's called acrylamide, and it is a fairly common one that is used in biochemistry. I don't know why, but I don't care. It's an interesting NMR sample. And then how we can get further information and confirm what we understand about our molecule from these 2-dimensional NMR spectra. We'll do a couple other examples of using these spectra, and the unknown for this module, you guessed it, is going to have all the different kinds of spectra, including the 2Ds. Again, you never start the analysis with the 2Ds. Always start with what we know. The protons, number of groups, integrations, all that stuff. Work your way up. Build your clues. Build the fragments as you go along, much like we did here. Oh, what a lovely, lovely logic puzzle this stuff really is. Oh, just love it.